Today we're going to talk about continuity. It's kind of the tail end here of our limits unit, as limits and continuity kind of go hand in hand. As you've seen, especially we've dealt with a lot of limits at places where functions had discontinuities, whether they were wholes or whether they were asymptotes, vertical asymptotes, things like that. So today we're going to really get into what the definition of continuity is and how we can determine what types of discontinuities we might find in certain functions. So this is going to be our second to last lecture for this unit, and the last one's next time is going to be on something called the intermediate value theorem, which also deals with continuity. We're going to start with a continuous function. What's a continuous function? Well, it's just a function that doesn't have any breaks or holes or asymptotes in it, right? You can go from the beginning of it to the end of it without picking up your pencil, right? That's a continuous function, right? If you have to pick up your pencil, it's not a continuous function, right? We consider a function to be continuous for its entire domain if it is continuous at every point C in its domain. And so in order to determine if a function is continuous at every point C in its domain, we need to know what does it mean for a function to be continuous at a point. Well, there are three criteria that have to be met for that. One, the point has to be defined. F of C has to exist. It has to be defined. Okay? Number two, the limit as x approaches C of f of x has to exist. And number three, those two things, the f of C and the limit as x approaches C of f of x, have to equal each other. And so there are three types of things that could happen at a point C for a function where we might have a discontinuity. So we're going to take a look at those three things on the next page and then sort of think about which of these criteria does it fail to meet. So our first type of discontinuity is a jump discontinuity over here in the top left. Jump discontinuity basically means what it sounds like, right? You're going along and all of a sudden you jump up to some other number, right? You have a jump in it, right? So that's a jump discontinuity. And so if we ask ourselves the three questions from the previous page here at C, we'll call C2, because that's where our jump discontinuity is happening. Does f of 2 exist? And the answer is yes. It's this point right here with the filled in circle there. That's our point, right? That's f of C. It exists. It happens to be 1 for this particular function. Okay. Second thing we'd ask ourselves is, does the limit as x approaches C or 2 exist? Well, in this case, this one fails to meet that criteria because the limit as we approach 2 from the left and the limit as we approach 2 from the right are two different numbers. And therefore, the limit as x approaches 2 of f of x does not exist. It does not meet that second criteria. Right below this, we have an infinite discontinuity. This is a vertical asymptote. We've talked about vertical asymptotes quite a bit already in this unit. Right, so we have a vertical asymptote at x equals 2. And so does this meet the first criteria? Does f of 2 exist? And the answer to that is no, f of 2 does not exist, right? So immediately there must be a discontinuity if we have a vertical asymptote. And then the third type of discontinuity is called a removable discontinuity. And those can kind of look two different ways. One is just a hole, right? And the other is a hole, but there's some other point. You can see down below here, we got this extra point added in there that I've sort of filled in now in blue, right? These are both removable discontinuities. So if you're asked to classify the discontinuity, either of these is removable. For the top one, does the function exist at 2? Does f of 2 exist? And that's the first criteria to see if it's continuous here. The answer is no, it does not exist. So this one doesn't meet the first criteria again. But for the removable one that's below, f of 2 does exist, right? We have a point there. 2, 3 is the point. And the limit also exists. The limit is equal to 2 from the left side and from the right side. We're approaching the same thing, right? But f of 2 does not equal the limit as x approaches 2 of f of x. It doesn't meet the third criteria. So it's still a discontinuity, right? You'd still have to pick your pencil up if you were to try and draw that function. Okay. So those are the three types of discontinuities that you want to be aware of, that you want to be able to recognize from just looking at a graph. But you also want to be able to figure out which of those discontinuities a function might have just given its equation by investigating the limits. And so we can use this information that we've kind of looked at right here to see, based on the limits, what discontinuity we might have. So for the jump discontinuity, the limit doesn't exist, right? The function exists, but the limit doesn't exist. And the limit from the left and the limit from the right are different from each other. Whereas for the infinite discontinuity, the limit as we approach 2 from the left or the right would have to be positive or negative infinity. And for the removable ones, the limit exists for both of them, but either the function itself doesn't exist or the function's value is different than the value of the limit. So this is what I've got written down here. Same idea of what we just talked about. A removable discontinuity exists. Those are the two on the right that we had. It exists at C if the limit as x approaches C of f of x exists, but either f of C does not exist or is different from that value of the limit. And we have a jump discontinuity if the limit as x approaches C from the right of f of x and the limit as x approaches C from the left of f of x are different real numbers. And then lastly, it's an infinite discontinuity if either of the values of the limit as we approach C from the right or left are either positive or negative infinity. So these three rules are going to be kind of important to us as we determine what type of discontinuity certain functions might have at certain points. So let's just investigate a couple of these functions. So here we have a piecewise defined function. F of x is 3x minus 5 when x is less than or equal to negative 1. It's x squared plus x plus 2 when x is between negative 1 and 2, and it's 4x when x is greater than 2. So the first thing that we'll look for is anything within these pieces that we know might cause a discontinuity. Now we have a linear, a quadratic, and then another linear function. Now, so regardless of what those linear or quadratic functions are, linear and quadratic functions are always continuous for all real numbers. So there's no just inherent discontinuities in this function. What we then need to check is what's going on at the places like negative 1 and at 2, where it changes from one piece of the function to another. So the first thing we'll look at is what happens at negative 1. And so we'll just kind of go through our 3-point definition of continuity. At x equals negative 1, first thing is, does f of negative 1 exist? Well, it says it's 3x minus 5 if x is less than or equal to negative 1. So yes, it does exist. F of negative 1, we use that piece of it. 3 times negative 1 minus 5 gives us negative 8. So we know that f of negative 1 exists. Its value is negative 8. The second thing we would check is, does the limit as x approaches negative 1 of f of x exist? And in order to do that, since we have two different pieces of the function that define what's going on from the left and the right at negative 1, we'll have to do a limit as x approaches negative 1 from the left of f of x and a limit as x approaches negative 1 from the right of f of x. Now from the left, we just did that. The left of negative 1 is less than negative 1. So that's the 3x minus 5 part. That's just negative 8 over here. And on the right-hand side, as we approach negative 1, when x is greater than negative 1, that's when we're approaching negative 1 from the right. So we would need to plug that into the x squared plus x plus 2. So we'd say, is negative 8 equal to negative 1 squared minus 1 plus 2? Well, I think very clearly there the answer is no. Negative 1 squared is 1. 1 minus 1 is 0. And 0 plus 2 is 2, which is certainly not negative 8. So that's not true. Therefore, does the limit as x approaches negative 1 exist? The answer is no, because we know that the limit from the left and the limit from the right don't equal each other. Okay? So at x equals negative 1, we had the situation where the left and the right-hand limits didn't line up. They were different values. And so that's a jump discontinuity. A jump discontinuity exists if the values are different real numbers. So we'll go in here and we'll say that at x equals -1, we had a jump discontinuity. Okay. Now let's go in and take a look at what's happening at x equals 2. So the first thing we'll ask ourselves is, does f of 2 exist? And immediately we'll look at it and say, well, this one says x less than 2. This one says x greater than 2. Nothing in there says what happens when x is 2. So we will know right off the bat that f of 2 does not exist. This function is not continuous at 2. It has some type of discontinuity there. It's not going to be an infinite discontinuity because a quadratic and a linear aren't going to cause limits of infinity or negative infinity. So our only options are either jump or removable. It'll be a jump if when we do the limits from the left and the right, they come out to be different numbers. It'll be removable if we do them and they come out to be the same. So let's see what the limit as x approaches 2 from the left of f of x is, and the limit as x approaches 2 from the right of f of x. Let's see if they are equal to each other or not. So as we approach 2 from the left, that'd be when x is less than 2. So we'll plug that in right here. 2 squared plus 2 plus 2. We want to know, does that equal? As we approach 2 from the right, that'd be x greater than 2. That'd be 4 times 2. So does 2 squared, which is 4, plus 2, which is 8, equal 8? Well, the answer is yes. So the limits from the left and the right are the same, which means it is meeting at that point. It's just that that point doesn't exist. Therefore, x equals 2 is a removable discontinuity. The limits from the left and the right were the same, but the function didn't exist then. Here's a slightly more complicated looking function. So f of x equals x minus 2 squared times sine x all over x squared minus 2x. So first off, let's figure out where the discontinuities might be. We can figure that out by figuring out what makes our denominator equal to 0. Right, there's nothing going on in the numerator that would cause any discontinuities. We can take any number, subtract 2, and then square it. We can take the sine of any number. But if the denominator is 0, we can't have that. So let's just set x squared minus 2x equal to 0 to begin with. We can factor out the x. That tells us that x is either 0 or x is equal to 2. Will give us a discontinuity. So we're going to have to look at limits as we approach 0 and limits as we approach 2. So we know that those are causing discontinuities. We know that f of 0 doesn't exist. We know that f of 2 doesn't exist. We don't need to check that. We just need to see what's going on with the limits there. So I guess let's start with the limit as x approaches 0. So we'll start here. We'll do the limit as x approaches 0 of f of x. And as we go through doing this, with any luck, we'll note that that denominator, in fact, let me write this out here before I say too much. That denominator that we had, that we factored over there into x times x minus 2, can allow us to cancel out an x minus 2 over an x minus 2, as long as x isn't 2, which it's not because, well, we're approaching 0, which means we're getting close to 0. So this should now become a limit as x approaches 0 of just x minus 2 times sine x over x. And from there, well, we should hopefully, with any luck, recognize that we can use a limit rule to turn this into two separate limits. One that's a limit as x approaches 0 of x minus 2, which I know how to evaluate, and one that's a limit as x approaches 0 of sine x over x, which I also know how to evaluate because that was one of our special cases. So the limit as x approaches 0 of x minus 2 is just -2. And the limit as x approaches 0 of the sine of x over x is just 1. That gives us -2. And so our function didn't exist, but our limit did exist, right? It was a real number. So if our function doesn't exist, but our limit exists, that tells us that x equals 0 is a removable discontinuity. So now we're going to have to go in and deal with what happens when x is 2. So let's go ahead and do that. So we're going to say the limit as x approaches 2 of f of x. Well, that's a limit as x approaches 2 of, well, can we make this same jump? Can I cancel the x minus 2 with the x minus 2 and just have a single x minus 2 up there? The answer to that is yes, because we can do that if x isn't 2, and it's not. It's approaching 2. So really, we're just going to be left with this, except it's going to be a limit as x approaches 2. So that will be an x minus 2 times the sine x over an x. And now at this point, we just see, well, can we just plug in 2? And does it become indeterminate? Well, the answer is no, it doesn't. Right? So we can just evaluate this. This is just 0 times the sine of 2 over 2. Well, I don't care what the sine of 2 is. I don't know what it is off the top of my head. It's some number. But if I take that number and multiply it by 0, I get 0. And if I divide that by 2, I still get 0. 0 is a real number. Therefore, my limit was a real number, but my function doesn't exist at 2. And thus, x equals 2 is also a removable discontinuity. So just real quick, let's take a look at what this might look like if we were to graph this in Desmos. So we got x minus 2 squared times sine of x. And we're going to divide all of that by, I believe we had x squared minus 2x. And so this is what that function, I get rid of that there. That's what this function looks like here. And it doesn't really look like there's holes in it at x equals 2 and at x equals 0, but we can see that if we get real close there at 2, the function is, lost it, 2, the function is undefined. And you can see that it's kind of making an open circle there. And the same at 0, the function is undefined, right? But we're clearly not going up to infinite values, right? It's clearly both removable discontinuities for this function. So let's take a look at another one that looks exceptionally similar, but is just ever so slightly different. Our difference here is in the denominator. We've got x cubed minus 2x squared. Everything else is exactly the same. So we're going to see how this affects this particular problem. So still, we'd want to set x cubed minus 2x squared equal to 0 and factor out the x squared this time, showing us that, yeah, still, the two things that are going to cause discontinuities for this function are x equals 0 and x equals 2. And so if we go in and try to do that limit as x approaches 0, or well, actually we did 2 first last time, right? So let's do our limit as x approaches, is that what we did first? No, we did 0 first. So we'll do 0 first again. So if we do our limit as x approaches 0 of f of x, that's the same as the limit as x approaches 0 of, well, it's x minus 2 squared times sine x over x squared times x minus 2 if I factor that denominator. And I can then cancel out an x minus 2 over an x minus 2 because x isn't 2. So we'll say this is equal to the limit as x approaches 0 of x minus 2 sine x over x squared. And now, if I try to separate this into two different limits, I can. One of them will be the limit as x approaches 0 of x minus 2 over x. And the other one will be a limit as x approaches 0 of sine x over x. And this is about as far as I'm going to be able to break this down here because, well, this second limit is just 1. But this first limit, if I plug in 0 to that, I get negative 2 over 0. Well, negative 2 over 0 doesn't exist, right? And in fact, if we think about this in a little bit more terms here, as we're approaching 0, depending on which side we're on, whether we're on the positive or the negative side of 0, this is either a positive or a negative, very, very small number, right? And so we're dividing by something infinitely small, which makes something infinitely big. So depending on which side we're coming from, this is either equal to positive or negative infinity. right? Because we just have -2 divided by an infinitely small number, right? And whether that number is positive or negative, it depends on which side we're coming from. We didn't do it as a two-sided limit. We could have done, as one-sided limits. We could have done each one-sided limit and found which side was infinity and which side was negative infinity. But that's not really pertinent to what we're doing. All we care about is it infinity or negative infinity? Yes, it is. Therefore, x equals 0 gives us an infinite discontinuity this time. And so let's see if the same thing happens when we deal with x approaching 2. So now we have a limit as x approaches 2, and our function f of x here, when we simplified it down, we canceled the x minus 2's, so we were still left with an x minus 2 times the sine of x. Right? And then in the denominator, we had the x squared. And at this point, if we plug in 2, just like last time, all these things are just numbers, right? This is just 0 times the sine of 2, which is just a number, over 2 squared, which is just a number. It's just 0. And so we still end up this time with x equals 2 as a removable discontinuity because we know the function doesn't exist there, but the limit does. And so if we go in, we'll real quickly go back and look at Desmos. The only difference here this time is instead of it being x squared, it's now going to be x to the third, and instead of it just being minus 2x, it's going to be minus 2x squared. And we can see how that's affecting us here. In fact, we'll make this even a little bit bigger. At x equals 0, we now can, I hope, clearly see that we've got a vertical asymptote there, an infinite discontinuity. Whereas at x equals 2, I can get that on the right spot, it's still undefined. It's still a removable discontinuity. So just that little change in the denominator has affected which type of discontinuity we have at x equals 0. And so that's going to be it for our classifications of discontinuities. We've got 3 types: jump, infinite, and removable. And we should know based on the limits what each discontinuity of a function, what type of discontinuity it's going to be. And that's going to be it for today. And next time we'll cover the intermediate value theorem, which will be our last section for this unit.